In this video, we're going to introduce some new terms and some concepts that will make the desired form, this triangular form that we've been talking about. We need to make that a little bit more precise, right? Because we've seen in some cases, particularly when a system has, let's say, more variables than equations, we can't really create that particular triangular form, right? So we have to have a more precise definition so you know exactly what to look for, right? So what I'm going to do is write down two augmented systems, and I'm going to have one that would be appropriate to use like back substitution, and then another one will illustrate the end result of Gauss-Jordan elimination, right? So let's say we have something like that, right? So that's one. And then let's say we have, now I'm not saying that these are equivalent systems by any means. I'm just writing down two general systems, and this one we can tell what the solution is. It has a unique solution. This one we would have to do a little bit of algebra to figure it out, right? And what we want to do is to introduce some terms and some concepts that will allow us to distinguish between these two in a very precise way. And then also, it would allow us to categorize augmented matrices that are in neither of these forms, right? Now, so the first requirement is that, again, and we've seen how useful it is, not just in the actual elementary row operations, but also in terms of back substitutions, like in a system that looks like this, where we would have to use back substitution. Having the leading coefficients, or my pivots, all be 1 is a very important thing. And in order for that to work, we have to have these entries below the pivots be equal to 0. And another way is, if you notice, to get that particular triangular form, we have to make sure that the pivots in lower rows are like further to the right, right? So for instance, the pivot in this second row is further to the right than the pivot in the first row. So it's almost like we have to go down on this almost like staircase kind of pattern in order for this back substitution to work. And then we have that same kind of pattern here. It's just that, again, in addition to eliminating entries below each pivot, we have to eliminate the entries above each pivot. So what I'm going to write down now is the definition of what we're going to refer to as echelon forms. And the word echelon here is referring to that staircase, stair step type pattern going down from the upper left to the to what would be our last pivot, right? So a matrix, an augmented matrix, I'll just say matrix, is said to be in row echelon form. And row echelon form is often abbreviated REF. So a matrix is said to be in row echelon form if these things have to be true, right? Now we haven't encountered this case or this particular property too many times so far, but any rows consisting entirely of 0 must be at the bottom of the matrix. So if every row filled with zeros, so the entire row is filled with zeros, right? Must be at the bottom of the matrix. So that row or those rows have to be the last rows going from top to bottom, right, of the matrix, right? After I've given you the definitions, then we will look at some other examples that kind of extend the properties that I was just highlighting here, right? So that's the first property, and there are three of them for row echelon forms. This one, I have to say, and I've done some extensive research looking at different books that introduce this concept, and it's not a consistent requirement, but we will be consistent and use this as one of our requirements. Every row with a non-zero term must start or must have a leading coefficient of 1, right? So each non-zero row, must have a leading coefficient of 1. And that's what we've been using as we go through our elementary operations, right? So must have a leading coefficient, also known as the pivot, right, of 1, right? So that's a requirement. Now, if we want to use this word to describe the specific form that phrase that our augmented matrix is in, right? And the third one is this, and this is the one that gives rise to that staircase kind of pattern going down from left to right. For two successive non-zero rows, right? The pivot in the higher row, or actually let me say it like this, the pivot in the lower row is further to the right than that of the higher, right? So then that of the higher. All right, so that basically says our pivots have to, if we start out in the left, they have to start out high, and as we go, we move from one column to the next, those pivots have to go down, right? So the lower the pivot, the further to the right it is, right? So that's a little bit more general because it allows for, again, those stranger systems, and we've looked at a couple where you might have more variables than equations or more equations than variables. We can still apply this definition because it has to deal with where the pivots are located, right? Now, so if our augmented matrix satisfies these three conditions, then basically what we have now is a system in which we can apply, or to which we can apply, back substitution. If we wanted to eliminate the need for back substitution, we have to add a fourth requirement, and that gives us an additional or another echelon form. So in addition to these three, so if, so let's say additionally, right? So in fact, or let me say it like this. This will be a better way to say it. In addition to, so in addition to properties 1 through 3, if every, so if every column that contains a pivot, right? So that's every time you have a leading coefficient of 1, which again has to be 1 because of our requirement here. If every column that contains a pivot, all other entries in that column is 0. So all other entries, well, let's just say are 0. Then the matrix is said to be in reduced row echelon form. Is said to be in reduced row echelon form, and that's abbreviated RREF, right? So, and again, this is simply just formalizing what we've been doing up to this point. So nothing new, there's no new process. So let me just list a few of these and say, is this an RRE? Is this an REF? Is this an RREF? Or is it neither, right? Or now obviously if a matrix is in reduced row echelon form, then it is also in row echelon form. It's just reduced even further because of the requirement to eliminate all the entries above and below the pivot. But let's take a look at something like this. And let's say we have 0, 0, 0, 0, 0, and 0, 0, 1, 2, -1. So this particular, let's say this is an augmented matrix, so I'm not going to draw the line there, but these are the coefficients. This one, it fails the first requirement because we have a row of zeros here, but it's not at the bottom. So this one is not in REF, right? And the reason is the 0 row is not at the bottom of the matrix, right? So what we would have to do, so let's say let's say we did a row swap on this one, and we would then end up with this. So let's say we swapped rows 2 and 3, right? And that would put the 0 row at the bottom like this. Now let's see if it passes the test, right? So definitely the 0 row is at the bottom. Every leading entry or term or pivot is 1, right? So that's good. And then the pivot in the lower row is further to the right. It might not necessarily be, where you would say, okay, it's kind of on the diagonal. Well, it's hard to say, to refer to a diagonal when this really, this rectangle isn't really a square, so you don't really have this nice diagonal. And that's why we have to generalize that particular requirement, that the pivot in row 2 has to be further to the right than the pivot in row 1. In fact, the pivot in row 1, it doesn't have to be in this position, and you'll see that in another example that I'm about to write down. But here, this matrix meets all three requirements to be in RREF. So this matrix is in row echelon form. So let me put the word in there. So it is in row echelon form, but not reduced row echelon form. Why? Because, so let's look at now the columns that have pivots. So there are only two pivots. Let me highlight them. Here are the two pivots, and we know those are pivots because those are the first non-zero row. The first non-zero entries in these rows, and they're both 1. And the requirement is all the other entries above and below pivots have to be 0. So check, check, check. Not good, right? So because of this entry, this matrix is not in reduced row echelon form, right? So I mean, we could fix it, right? In my other example, we could do something like this: make that a 0, and then 0, 0, 0, 0, 0, and now this is in reduced row echelon form, right? Now you might say, well, if this is in fact a system, right, what would the solution look like? So I'm not going to write it down entirely, but I'll just give you a hint. So now let's say this is your column of B's, right? So these are the constants. So this is telling me that we have a system that has 2 equations, right, but 4 variables, right? Because, you know, the first column would correspond to x1, the second column to x2, the third column to x3, the fourth column to x4, and then again, this is not an x5 thing, these are the B's, right? But so here we have a system that's in one of our special forms. It is a triangular form, but more so it's an echelon form. But there are more variables than equations, and this is where we end up with free variables. In fact, the number of free variables would be equal to 2. So it will have 4 minus 2 free variables or parameters. What would those be? Those would be the variables that don't have a pivot in their column. So the 2 free variables would be x2 and x4. There is not a pivot in column 2, and there is not a pivot in column 4. Again, let me circle the pivots for you, right? So then you would label this as x. You'd say let x2 equals t, let x4 equals r or s or some letter like that, and then you'd be able to solve for the pivots in terms of those free variables, right? So and again, that's a process that I know we will do a lot of it going forward. So I don't want to focus too much on the parametric stuff now, but just on the notion of the echelon forms. Let's do one more example, just so you can get a sense of what's going on. And you can have strange things that look like this where you don't have a pivot at all in the first column. Sometimes, what if you start out with a system where all these coefficients are 0, right? No matter how many times you do or try to swap rows, you'll never be able to create a pivot of 1. So your pivot could actually start there, right? And then, so this is a system that will have several variables, let's say like this. And then again, just to emphasize where that pivot in a lower row could be, it could be really further over. It could be something like this, right? And then, you could have something like that. Let's say that's 10. And then let's say at the bottom now you have your row of zeros, right? So this, again, is in REF, but not RREF. And why is that the case, right? So let me write that down. So this one is in REF, but not RREF. Oh, I have too many R's there. And okay, so let's go through the requirements. I'm going to highlight the pivots. So here's our first non-zero entry in the first row. Here is the first non-zero entry in the second. Here is the first non-zero entry in the third. And again, each time we go down a row, we go further to the right in a column to find the next pivot, right? So that's good, and they're all ones. Zero row is at the bottom, perfect. The reason why it's not in RREF, right, you might want to take a guess, is because of this entry and this entry. In a column that has a pivot, all the entries below have to be 0, so those pass the test. But then in RREF, all the ones above a pivot also has to be 0. So this is good, but these two are not, right? So, take a few minutes and think about read through the definition carefully and think about the how they differ. But again, you might be wondering, why do we even need to classify matrices in using this particular form? It's because this is a form that comes from either Gaussian elimination or Gauss-Jordan, depending how far we take it. So, if we want the ability to look at a particular augmented form and say to ourselves, yep, we've reached an echelon form. And once you're in an echelon form, it means that writing down the solution or obtaining your solution set is just a few steps away, right? And the more reduced the echelon form is, like RREF, then the easier it is to write down the solution set, right? So even though this seems like kind of an abstract definition, it's still tied back to linear systems and how we can express the solution, right? Good stuff. Think about it. I will see you sometime in the future.